Bismillah ar-Rahman ar-Rahim. Welcome to this lecture, which will be a problem-solving session. And tonight we are going to solve 6 problems, inshallah. The first problem is, and the topic, the master topic is about Unit 9, which is functional blocks and MSI components. So, yeah. So this is the first problem. Let's try to understand the requirements first and then try to solve it. So you are given that we have this kind of multiplexer, 4-to-1 multiplexer with external signals as well as internal signals here, okay, shown to you with the external selection lines. So we would like to implement this multiplexer, okay, 4-to-1 multiplexer using the constraints given below, okay, using these components. First of all, you can use only 2 units of 2-to-1 multiplexers, okay, and you can use 1 decoder and 1 OR gate, okay. So the usual way of doing this is to use multiplexer expansion, and then if you want to do that, if you want to expand this 4-to-1 multiplexer using 2-to-1 multiplexers, you'll have to use 3 2-to-1 multiplexers, okay. But here you are constrained to use 2 multiplexers only, 2 2-to-1 multiplexers. So this is a trick, okay. Again, here this is some what we call standard text that you should be aware of in your circuit. Make sure that you label all your components from inside and outside, okay. Also make sure that the external interface signals x0, x1, x2, etc., w1 and w0 and z are clearly shown and labeled in your circuit. Right. Okay, first of all, let me show you. Okay. Let me show you the implementation of this multiplexer using 2-to-1 multiplexer. So first of all, z, if you want to write it down algebraically, what does it equal to? It equals, first of all, we have the selection lines W1, W0, so W1, W0, complement, complement, and if this is the case, then we select X0, okay? And if this is not the case, then we select W1 complement, W0, and we select X1. Otherwise, W1, W0 complement, then we select X2. Okay, this is the multiplexer, a 4-to-1 multiplexer Boolean function. It's as simple as that. Okay, and then finally W1, W0, and then X3. Okay, so we are going to select X1, X0, X1, X2, X3 according to the selection lines, and these basically expressions are basically the min terms of the selection lines, okay? Right. If you take a common factor here between the first 2 terms, first 2 product terms, W1 complement, what are you left with? W0 complement, X0, right? And the second one you have W0, X1, all right? Okay, so the second one is W what? 1 without a complement, so this and this, W1 without a complement, and then you have what? W0 complement, X2 ORed with W0, X3. Right. Okay, so you can see that this is a 2-to-1 multiplexer. This is a 2-to-1 multiplexer. Okay, and the whole thing is a 2-to-1 multiplexer. Okay, so we have a 2-to-1 multiplexer at the end here, where the selection line is W1. Okay, this is the external. This is basically this one, selection line of this one. If this is selected, then we are going to have line number 0. So we are going so we used one of the 2-to-1 multiplexers now. Okay, so if this is if W1 is 0, okay, then we are going to come from this side. Okay, so we are choosing either X0 or X1. Okay, X0 or X1, X0 or X1, and the selection line is going to be W0. Okay, now you have exhausted your 2-to-1 multiplexers. You are only, what you can do is to implement the rest using a decoder. Okay, so we want to implement this function using a 3 to 8 decoder. Okay, so this function, so you have like a function G. Okay, I'm going to write it down here. So G of, let's say, W0 comma X2 comma X3 is equal to what? It equals W0 complement X2 ORed with W0 X3. What are the minterms of G in this case? This one has two minterms, which is basically 0, 1, 0 and 0, 1, 1. Okay, this is minterm number 2, and this is minterm number 3. Okay, and for this one, it is what? It is 1,
1, 1.
Yeah, 1, 0, 1 and 1, 1, 1. Okay, which is minterm number 5 and minterm number 7. So what do we have here is basically 4 minterms that we need to OR together in order to create our G, right? So what are we feeding here? We are feeding G, okay? So this G is coming from an OR gate where these minterms are ORed, okay? And how do we create these minterms? Using 3 to 8 decoder, and where 2 to the 0, 2 to the 1, 2 to the 2, okay? So this is basically, I forgot to, so it's 2 to 1 max, okay, 2, 1 max. You have to label your component. And this is, because I don't have space here, this is a 3 to 8 decoder, okay? And I don't need to write down all the outputs. I only can write down the outputs that I need. I need the D2 and D3, D5, and D7, okay? And then I'm going to OR these together to get my G. Okay, what do I hook up to these lines now? 2 to the 0, I need to hook up the least significant bit, which is X3. And then 2 to the 1, X2. And 2 to the 2 is the most significant one, which is W0. Okay? All right. So this solves the question, okay, completely. All right. Of course, you can have another solution. If you, for example, take, instead of taking here W1 as a common factor, you can take W0 as a common factor, okay? And then you'll wind up with a different solution with respect to the selection lines, as well as the order of probably the X0 and X1, as well as the order of the minterms that you are going to select, okay? So these are variations of the problem. All right. So moving on to the next problem.
Doctor?
Yes.
Sorry, can you just explain how did we transfer to the left side to implement the decoder?
You're talking about this one?
Yes.
Okay, this one is nothing but this. I'm assuming that this is G, right?
Okay.
Exactly, this is G. This is I'm just equating this to G, a function called G, okay? And then listing the minterms of this. Okay, assuming that W0 is the most significant variable, then X2, then X3, because this is a function of the W0, X2, and X3, right?
Okay, yes.
W0, X2, and X3. Okay, so this equals to what? W0, X2, W0 complement X2, ORed with W0, X3, and then just express it in canonical forms, extract the minterms like this, okay? And then use a decoder to realize this function, G, okay? And G is nothing but the other input, line number one of this data line number one of this multiplexer. Okay, so this is going to be my Z. Okay, all right. Any other question, Amar?
No, clear.
Okay. So the other question here is basically we would like to show an implementation of this function using a 4-16 decoder. The only trick here is that you are given a 3 variables function, so you are supposed to use 3 to 8 decoder, not 4-16. Okay, but again, you can create a dummy variable f of a, b, c, and d. Okay, but it is going to be much easier if you create the variable as and make it like your most significant variable, because then the midterms will not change. So I'm going to create b and make it my most significant variable, a b d a b c. Okay, and it equals the same function a b ORed with b complement c, and then you create the midterms. Okay, so we have dash 1 1 dash, right? Yeah, because dash, this is not mentioned here, and this is not mentioned. Okay, so we have dash 1 1 dash. Okay, this can be either we have 4 values here, basically basically 6. Okay, so this is going to be 0 1 1 0 comma 0 0 1 1 1 and 0 actually no 1 1 1 0 and 1 1 1 1. Okay, so these are the midterms covering this product term. Okay, and this one, what is the product term in hyphen notation? Basically, we have
dashes, 0.
Yeah, hyphen, okay, hyphen 0 1. Yeah, hyphen 0 1. So it is basically 0 0 0 1, and then 0 1 0 1, and then 1 0 0 1, and then 1 1 0 1. Okay, so our function f of d a b and c is going to be the sum of these midterms. So we have 1 5 9 13. Okay, and then here we have 6 7 14 and 15, right? Okay, so ordering them 1 5 6 7 9 13 14 and 15. Yeah, okay, so how many turn 1 2 3 4 5 6 7 8. Okay, so it's exactly half the total number of possibilities. Okay, so there is a tie here. So using the expressing the function or its complement is the same. Okay, it requires the same number of inputs for the OR gate. Okay, so all you need to do now is to create a 4 to 16, which is boring, 4 to 16 decoder. Okay, and then so this is 2 to the 0, 2 to the 1, 2 to the excuse me, 2 to the 3. Okay, and for line number 3, I connect D, and then 2 is A, 2 to the 1 is B, and finally C. The least significant one is C. Okay, and this is a what? A 4 to 16 decoder. I'm not going to draw all the D's here, D1, only the ones that are needed, D5, D6, and D7, what is it, 9, D13, D14, and D15. Okay, so you take all of these and you create a big OR gate. Okay. And this is going to be your function f. Okay. All right. So this is like a trick that you can get. Okay. So do not get confused if you are asked to, use a larger size decoder than needed. Okay. And this is nothing but creating a dummy variable that is not used. Okay. All right. Any question, Amar?
Clear.
Okay, so given this Boolean function, this is problem number 3. Given this Boolean function, okay, show an implementation of G using only a 2-to-1 multiplexer and nothing else. Okay, this is a trick question. Okay, and we gave it in an exam previously, and only a few students solved it. And it is basically it requires very sharp observation, because if you try to implement it as is, you are going to need more than 2-to-1 multiplexer. But if you have a good observation, then you'll observe that this term here is redundant. Why? Because it's the consensus term between this term and this term. Okay, so this is redundant. Okay, so the function actually equals y complement x ORed with y z. So you are selecting either x or z. Okay, depending on y. So y is your selection line, and you are selecting either x or z. So we have a 2-to-1 multiplexer like this, okay, 0, 1, and the selection line is going to be hooked up to y, and when y is 0, I'm going to select what? X, and when y is 1, I'm going to select z, okay, and my output here is G, okay, and this is a 2-to-1 max. Clear, ya Amar?
Clear, very direct.
Yeah. All right, so problem number 4. Okay, we are going to use MSI components only without any logic gates. And we would like to implement a circuit that converts from XS3, given XS3, to BCD 8421. Okay, 8421. All right, so we know that XS3, this is given to you here. Okay, XS3. If you are given XS3, then your BCD is going to be, you have to subtract 3 from this, such that this is your BCD. Okay? All right, so what is the range of XS3 values? What is the range of XS3 values? XS3 ranges from 0 plus 3 all the way to 9 plus 3, and this is equal to 3, and this is equal to 12. So these are the normal or the valid digits of XS3 code. Okay, the minimum value is 3 and the maximum value is 12. It cannot be any other value other than these. So if you get a 0000 as XS3 code, then this code is in error. Okay, this code is in error and it's not accepted. Okay, so what are we? There are many ways to implement this this circuit. Okay, one way is to use decoder encoder circuit. Okay, decoder encoder circuit. So we have a 4 to 16 decoder. Let me just draw that 4 to 16 decoder. Okay, and I'm not going to draw the whole thing. Okay, but you get the idea. Just 4 to 16 decoder. And its input is going to be 4-bit, of course, 4-bit, all right, and it is going to be the XS3 code, okay, XS3 code, all right, and the outputs are going to be D0 all the way to D15, okay. However, we know if the X3 code is valid, then only D3, starting from D3, is going to be on, okay? Is going to be, I mean, possibly going to be 1. D2, D0, D1, D2 are never going to be 1 because they are not, they don't correspond to, they do not correspond to valid X3 code, okay? So the first one is D3, and when you have D3 on, then your X3 is 0011, okay? And this X3 code corresponds to, subtract 3 from that, you get 0000. So it corresponds to it corresponds to 0 in 0000 in BCD 8421, okay? So if I have an encoder, a 16-to-4 encoder, 16-to-4 encoder now, okay? And I take D3 here and I feed it to D0 here. What do I get as an output? Or which is basically, this is going to be the BCD code, okay? Because if I get here 3, if I get in this side a 3 in this side, then this output will be 1, and this 1 here is going to create an output here that is all zeros because D0 is has been 1, okay? So remember, the decoder, one of the outputs will be 1, okay, and then the encoder, it tells you which output, which input has been 1, okay, which input has been 1. So in this case, it is D0, okay. So what if D4? What if D4 is 1? What if D4 is 1? If D4 is
D1.
1, yeah, where do we put it?
D1.
Excellent, D1. And so on and so forth. You get the idea, right? If D5, then it is D2. So basically, we subtract 3 from the index, and so on and so forth. And the last value is D, what? 12. Okay, this is the maximum that you can get in X3. Okay, and this is going to be connected to D9.
No.
Yeah. So this is like the circuit. Any question, yeah, Omar?
لا الحمد لله كذا.
Okay. Omar, feel free to, if you want to, if you have something to do or you have to leave, like your colleagues, of course, you can leave them. No hard feeling, okay?
أبشر.
Yeah, but just stay if you want, okay? Stay if you want, because the lecture is not mandatory, okay? Yeah. Anyway, we are. I think this is the last problem. So this is last thing. Okay. So we in problem 5 we are going to construct an arithmetic logic unit that takes 2 signed numbers, A and B. Both are 4 bits and they are signed in 2's complement. And the ALU is supposed to produce Z output according to the function selectors F1 and F0, okay? And this is the table for the functions, okay? So if the function is 0, 0, then you subtract 5 from A, and this is your Z, okay? If the function is 0, 1, then you just add 6 to B, and this is your Z. If the function is 1, 0, then your Z is going to be the maximum of A and B plus 1, right? If the function finally is 1, 1, then you are going to negate A, add that to B, and then subtract 1, and this is going to be your Z. All right. So we know that we are performing arithmetic in 2's complement. Okay, so we can just do it on the side here. So minus 5 is minus 0, 1, 0, 1, and that in 2's complement is what? We have a 1 here and then a 1, 0, 1. Okay, that is minus 5 in 2's complement, right? So we just took the 2's complement of plus 5, to get -5. So this is going to be A plus 1, 0, 1, 1. Okay, and this one is B plus 0, 1, 1, 0. This is just a positive number which doesn't change. Okay, it has the same binary information, binary representation. Okay, the maximum is going to be the maximum coming from a comparator and the multiplexer. Okay, the maximum plus 1. Okay, and then finally minus A is going to be a complement plus 1, and a complement plus 1. The plus 1 will cancel with the -1, and you will end up with a complement plus B, right? So there is the this is your circuit now. So you are going to have 2 4-to-1 multiplexers. Okay, selecting either this or this. Okay, and then you will forward this to one input of the adder and this to the other input of the adder, and then you get your circuit. And notice that you are required to use only a single adder. Okay, you cannot use more than one adder. Okay, so we need a 4-to-1 multiplexer, actually a 4-bit 4-to-1 multiplexer. So it's called a quad 4-to-1 multiplexer. So we have this multiplexer here, 4-to-1. Okay, line number 0, 1, 2, 3. This is a 4-to-1 max, and it is a 4-bit. Okay, and we have selection line number 1, selection line number 0. All right, and we know that a line. Okay, these are going to be connected to the function selector F1, F0. All right, and then if there's 0, 0, then we select line number 0, which is a 4-bit. Okay, and it is going to be A. If it is 0, 1, then I'm going to select B. If it is 1, 0, then it is coming from another multiplexer that selects between A and B. So this is line number 0, line number 1, and it is a 4-bit 2-to-1 max. Okay, this is S, and it is selecting between A and B, the maximum of A and B. Okay, this is going to be the maximum of A and B. So if I'm going to select B if B is greater than A. Okay, so the selection line is coming from a comparator, for actually a signed comparator. All right. So this is assumed to be a block. There is a comparator somewhere. Okay, we'll have to draw it when we finish. Okay, to make sure that we get this signal from the comparator. Okay, and the third case is a complement. Okay, so this is going to be a complement. All right. Next, we can draw this. Instead of drawing it again, I can just copy this and paste it below. Right. And for the first one, we will have this 4-bit number, which is 1, 0, 1, 1, which is -5 in 2's complement. Okay, and the second one is going to be 0, 1, 1, 0. Okay, and the third one, let's this one here, we can have it as a carry in. Okay, carry in for the adder. Okay, or you can also why not? Let's just have a 1 instead of all zeros here. Okay, yeah. So we just have it as a 1 here. So the carry in is always going to be a 0 in our case. Okay, of the adder. And the final thing is B. Right? B. So this is one way of implementing this function. Okay, or this ALU. You may wind up with a different solution. So the way this is done is will have some creativity, and it will differ from one person to the other. Okay, and some solutions may be better than others. This is the carry n. The carry n is always 0, and this is A and this is B. So this is a 4-bit, and this is 4-bit, and this is a 4-bit ripple carry adder. Okay, and the sum is going to be your Z. Okay, and the carry out is going to be ignored. Okay, so this is your function. Okay, any question, yeah, Omar?
ممتاز.
Okay, yeah, I think I can stop here. Okay, because unless you have a question, yeah, Omar, in like other topics, I will stop here. Maybe someone else.
بس إذا تسوي طريقة اللي هو الكاري ان اللي قلت عنها كيف طريقة
carry n, yeah, if you want to do it using the carry n, then you just raise this and have all zeros here. Okay, and then here, oh, this is too big. Here you'll have a 1 only at this function, which is the third function, which is when f1 is 1 and when f0 is 0. Okay, so you have like AND gate, which detects f1 being a 1 and f0 being a 0. In this case, you'll have to add a 1. Okay, add a 1 as shown here. Okay, you have to add a 1 for the maximum of A and B. And the other side here is 0. So this is one solution. I mean, there are many other. You can have many other solutions. Maybe this solution is not the most optimal, by the way. If you think about it a little bit, you can also have some, you know, this thing here is all zeros. So you may wind up with a much simpler circuit in your implementation. And this thing here is a constant. So you may have some design, contraction in your circuit. So much contraction. So this 4-to-1 multiplexer may not be the most optimal way, but this is something that works. Okay, it works. One implementation. Okay, yeah. So that's for the problems. Okay, I don't want to take much of the time, and I will probably record my other sessions offline, because you know no one wants to attend, and they will be uploaded regularly to the YouTube list. So just keep watching that, and hopefully. And by the way, the last video in the current last video in the YouTube list, okay, which is the video before this one, it's supposed to be before this one. I'm going to add this one to the playlist. The video before that contains a number of problems on what we call state diagrams and sequential circuit analysis and design. So make sure that you watch that, because I'm not going to repeat the problems there. They are there for you if you want them. And I'm going to probably discuss more difficult problems in the next session for the state diagrams as well as registers and counters. Right. Okay, let me stop here so that the video does not get longer than that. I'll stop recording.